So, how we doing, folks? Getting ready for this review. We want to make sure that we have all the information we can to prepare for this test. And that's what these reviews are about. This Unit 4 on recursion, lessons 2 through 6. Unit 5 on functions, Unit 1 through 3. So question 1 says, what are two things that one must know in order to create a recursive or explicit rule? Okay, for recursive, you definitely have to have two things, okay? So a line moves in such a fashion, we learn in algebra, that when x moves a certain number of moves, y moves a certain number of moves. So what is the rise over run? What is the slope of what happens to y every time x moves 1? Or in this case, when we're talking about explicit and recursive movements, what happens to a, which is the value of the number in the sequence, when n moves 1, which is the number in the sequence? So we need to know two things in order to best create recursive or explicit rules. Let's start with the first one, the common differences of the variable. It's very important, okay? The common difference of the variable is important. We have to know what changes. It's the slope, okay? We also need to know what is the initial value. What is the initial? Let's write this correctly. We don't have to. The initial value. So where does it start? What is the first value in the sequence? So for instance, let's say we have a line that has a rise over run of 1. So when x moves 1, y moves 1. So that means that we can write the slope, but we have to know where it initializes. So where does it start? So if we started to, let's say we're going to add $10 to our bank account every month, well, it would be nice to know how much is in the bank account to start with. So that is our y value when we haven't added anything. So let's say we started with $250 and we're going to have $50 every month. In 1 month, we'll have $300, and in 2 months, we'll have $350, 3 months, $400, and so on. So it's very important to know those two things. All right, second question. If a linear equation has a common difference, what does an exponential equation have? Well, we're multiplying every value of n, so or every value in the sequence after the initial value. So we have to know what the initial value is. Common differences change linearly. Common factors or constant of proportionality, whatever you want to call it, are used to determine the next value in the sequence in an exponential equation. Or, when it comes to exponential equations and recursion. All right. Say an algae grows in an aquarium that has an 8 square foot of surface area on the inside, and it grows at a ratio of 15% per day. What is the limit of growth, and which recursive routine would best fit this growth? All right. So the first thing we need to know is how much algae does it begin with? Well, we're assuming that there's none when it starts. So that means that the amount of area that the algae covers in the beginning is 0 square feet. Okay? But that doesn't mean anything. It changes. We have a 15% growth every day. So we have to use which recursive routine to best fit this growth. So what is the limit of the growth? Well, that's pretty simple. The algae cannot grow on anything but the surface area of the inside of the aquarium. So the limit is limited. The limit is the surface area of the aquarium. But the best routine we can use in recursion is called the restricted growth recursion routine, okay? And we briefly went over this in the very last section in Unit 4. I want to make sure you understand what that means. So there's an equation we use that restricts the growth based on the limits in which it is given. In this case, 8 square feet is a limit. So we're not given an initial value, so we're not asked to do anything. We just need to give our answers to this question. All right. We're going to find the 753rd iteration of a linear sequence. Is it easier to determine by recursive or an explicit rule? Okay, if we're going to do 753 iterations using recursion, we have to start at 0 and do 753 computations. I think that's kind of redundant. Why don't we just put 753 in the equation to find the answer? Well, there you go. The explicit rule does that. You can simply place 753 into the equation to find the answer. All right? So that's our best answer for that. All right? Finding the first 10 iterations of a sequence is easier to determine by using recursive or explicit rule. Now, an explicit rule, we'd have to put every iteration into the equation to find each value. Wouldn't it be simple to just start at the beginning and make the iteration done once we find the next one? It's simpler to do that. We're accustomed to doing what we call Q values, or values that change based on the last value. So recursive rule, because all you have to do is simply use each answer to determine the next answer until you have all 10 iterations. All right. Question 6. Given the sequence 7, 13, 19, 25, if the first value, a subscript 1, is 7, what is the value before it, a subscript 0? Well, first of all, we got to find the common difference. What's the difference between 7 and 13? It's 6. What's the difference between 13 and 19? It's 6. What's the difference between 19 and 25? It's 6. So we're talking about a sequence that changes using a common difference. So this is a linear recursion routine. The recursion routine is pretty simple, and we'll talk about that in part B. But if it changes 6 every time, if we're going back 1, we have to subtract 6. So because the common difference is 6, we determine it that way. A0 is 7 minus 6, or 1. And that is the answer for question A. What is a recursive routine or a recursive rule? It's pretty simple. We know that A0 or A1 is 7 because it's given right here. What do we do to it every time? We add the common difference D, which is 6. So AN plus 1 equals AN plus D. And there's your answer, where A1 equals 7. Okay, I'm going to change that to the right color so you can read it. And there you go. What about an explicit function rule for the sequence? So what can we do to the answer? First of all, we know the common difference is 6. We add that to the value that it starts with. Okay, so AN has to equal what? AN minus 1. What is done to AN minus 1? All right. Well, we're not going to do it that way. That's recursion. In this one, we're going to look at what AN is based on what N is. So what are we doing to N? We're going to start where AN equals whatever we're doing to N to make the value. So if N is 0, we know that A0 has to be 6 or 0 or 1. So what do we do to it? We're adding 6 to whatever 0 is, okay? We got to start somewhere. Let's get what it looks like. AN equals 6N plus 1. That's right. So whatever N is, we're multiplying it by 6. So if N is 0, we multiply 0 by 6 and we add 1. And that's what it is. Well, if A is 1, we multiply 6 times 1 and we add 1, and that's 7. If N is 2, we multiply 6 times 2, and that is 12 plus 1 is 13. So we're getting the sequence using this. We don't have to give what the initial value is in the explicit function. And we do, it's going to be 1 in that particular instance, but D in this case is going to be what? 6 from 7. The initial value would have been 1. However, we started at A1 over here. So complete the given table for a ball with a rebound percentage of 45%. So the initial bounce or drop height is 215 centimeters. So we're going to multiply this 215 times the rebound percentage in its decimal equivalency. And as you can see, what happens here is we multiply just 215 times 0.45. All right. And that comes out to 96.75. And to find the second bounce, we just multiply this value, 215 times 0.045, times 0.045 again. which is 215 times 0.045 times 0.045, which equals 96.75 times 0.045. And that gives us a value of, if I'm not mistaken, 43.54. Okay? Oh, that don't work. It would be nice if it did. There we go. 215 times 0.045 times 0.045 times 0.045. We do it 3 times, which is the answer in the last column times 0.045. And that gives us an answer of 19.59. Fourth bounce, we just multiply it by 0.45 4 times, or raise it to the 4th power. And that gives us an answer of 8.82. Fifth bounce, we're going to multiply that common product or common factor or constant of proportionality, which is 0.45, 5 times. And that gives us an answer of 3.97. So there's your chart all filled out. We're going to write a recursive rule for this. Well, what's the initial value? It's 215. So we know A0, or the height 0, whatever variable you use, is going to be 215. What do we do into 215? So what do we do in the last value? We take the next value, which is AN plus 1, is equal to this value, A0 times 0.45. That's all we're doing. And if I'm not mistaken, I think that's the answer I got. That's absolutely right. AN plus 1 equals AN times 0.45, where the initial value, A subscript 0, is 215. How about explicit rule? Now, we went into this, and it's just an exponential function is all it is. It's 215 times 0.45 raised to the n power. If I'm not mistaken, and that's correct. Your initial value, 215 times 0.045 raised to the n power. What is the height after the 4th bounce? It's dropped from 525. Now we change the initial value, so we have to change that. It's 21.53. We just put it into the exponential function. How about if the ball is dropped from a height of 260 centimeters? How many times does it bounce before it has a bounce height of less than 5 centimeters? Now this one's kind of difficult, but I'm going to be honest with you. It's probably best to plug and chug, and that's what we did. We looked at it from a perspective of how many bounces. So we start at 0. 1 is 260 times 0.45. We had all these answers. We go all the way to this to 4.8. So 5 bounces until it rebounds less than 5 centimeters, which is 4.8 centimeters. I complete the given table for Jim Bob's savings account. He deposits $150 and gains 5% interest every month, and he adds $50 each month. He had deposited $150. That's what initially was in the account. He's going to gain 5% interest on it, which in this case, it's the $150 plus the 5% interest. So it's you multiply 150 by 1.05, and then he's going to add $50. So that's the process he uses here. And let's see what that looks like. So it's $150 times 1.05 plus $50. And that nets him, as you can see, $207.50. Because it's $150 plus $15. Is that right? No. $150 plus $7.50 plus $50, which is you add $57.50 to $150, you get $207.50. Now we're going to do the same thing, but this time in the next month, we're actually doing it to $207.50. We multiply that by 1.05, and then we add $50. And that nets us $267.88. This time we made a little extra money instead of the $7.50. I think we made more like $12. Not sure exactly what, but just suffice to say, the mathematics are correct in this. If you use a calculator, and I'm going to show you how to do this after we build this table. Do the same process to the $267.88, and we come up with $331 and some change. On the 4th iteration in the 4th month, He's going to add 5% plus $50, and that brings him up to, should be around almost $390. Oh, it's $397, almost $400. I apologize. When we finally do it to that $397, you add 5% and add $50 also, and you end up with, after 5 months, $467.72. Okay? So, then I'm going to be honest with you, you're not going to find a bank account that gives you 5% interest every month. Okay, now I got my calculator up, and we'll show you how this works. So, initially, the first amount of money we have in there is $150. So we're going to put $150 into our calculator, hit enter, so it's there in the memory. And then we're going to multiply by 1.05, and then we'll add $50, okay? So because of PEMDAS, the calculator does the multiplication first, then the addition, okay? So 207.50. Now, the best part about this calculator, I'm going to take this answer, and I'm going to do the same thing. Okay, I should be able to hit enter and get the same thing. See, now I've got, it's using what's called recursion. It's recursing the same routine. Answer times 1.05 plus 50 plus 1.05 times 50. I'm getting the same answers that I have in my chart. So as you can see, that routine works well in a calculator. As long as you have the routine typed out to multiply against the answer, you're going to get the same routine against it, okay? All right, so they want us to write a recursive rule for this relationship. So in recursion, remember, we're looking at what do we do to the last value to create the next value? We multiply by 1.05 and we add $50. So whatever the next value is, we'll call it A subscript n. We do something to the last value, A subscript n minus 1. We're going to multiply that by 1.05 and add $50. And if you see in this next one, that's exactly what it says. And we start where the very first value is $150, okay? So as you can see, it's the answer, whatever the answer was in the last one, times 1.05 plus 50. So I used the recursive rule to create this recursive routine in my calculator. An explicit function. Now, because of this $50 right here, there's no way to describe this as an explicit function. It's just impossible. To be quite honest, you could write it, but you'd have a different formula for each iteration because you're adding the extra $50 to what you put interest on the month before. It's a series function, so recursion is best described to this. So really, to be quite honest, there is no explicit rule. There's no way you could just plug in n to one simple function that would give you the answer regardless of what it was. There you go. There is no explicit rule that describes this relationship. Now, how much money will they have after 12 months? Well, this is complicated. You actually have to just continue the process. I'm going to show you how I got that number here in just a second. I'll pull up my calculator. The chart goes up to the 5th month. So all I have to do to find the 12th month is I just have to keep doing this routine over here 12 times. Now I've done it 5, so 6, 7, 8, 9, 10, 11, 12. And there you have it. 1,065 and 23 cents. I got this answer from. And how long will it take to have $3,500 in order to make a down payment on a new truck? Well, you got to just continue doing it until you get to $3,500. In 28 months, he'll have $3,508.15. How long will it take him to have $3,500? Same thing, keep going. I'm at 12 months. We have to go until we get above $3,500. So it's 28, right? Let's see if that's correct. 12, 13, 14, 15, 16, 17, 20, 25, 26, 27. There it is right there, 28. 3508 and 15 cents. I rounded. Now in this process, how much more must Jim Bob add monthly to get his down payment in 6 months? There's no way to algebraically answer this question. You have to plug and chug. To be quite honest, you could do it algebraically. It's kind of pointless, but I did the plug and chug method because it actually, or trial and error method, you'll find that if you add $411.50 to his account, and in addition to the 5% in 6 months, he has exactly $3,000. I actually I did what's called shot and a half. I'd go over it, and if I went way over it, I'd go as far down below as I thought I needed to get below it, and I get below it, and then I'd kind of get in between until I got there. Okay? So let's go back and look at how to do this on the calculator. Give me just a minute, and I'll show you how that's done. Now, as far as the trial and error method, you have to find out how much more you have to add. So I'm going to start at 150. Put that in as the answer. Got to hit enter. And then multiply your answer times 1.05. And then you got to figure out what you have to add to it. And what I did was I started with 250. And I wanted to see how much it would be after 6 months. 1, 2, 3, 4, 5, 6. It only went to 1900. So I went to 500. So 150, not 10, times 1.05 plus 500. How much will that be after 5 months? That's 1, 2, 3, 4, 5, 6. Well, it's $3,600. It's $600 more. Adding the $500 didn't help. Just the 1.05 put me over the edge. So I need to go under. So let's try 400, which is what I did, times 1.05 plus 400. Oh, there we go. Mess that all up. Times 1.05 plus 400. 1, 2, 3, 4, 5, 6. I'm just under by $78. So let's see. 410 is what I think I did. Times 1.05 plus 410. $410. 1, 2, 3, 4, 5, 6. Look, I'm under by like $10. Just a little more than $10. So I'm going to try $11, which is what I did, times 1.05 plus $411. Not 500, 400. Uh-oh. Let's try this again. Times 1.05 plus $411. 1, 2, 3, 4, 5, 6. Man, I'm under by $5, $3.40. So I tried $411.50, which is exactly the answer, and we'll see how that works out. So that's $411.50. 1, 2, 3, 4, 5, 6. $3,000 exactly. So that's how you use the trial and error method, and that's how I got my $3,000 as my answer. Okay? So, all right, so last question on this review. We're looking at a chart, the recorded heights for each ball bounce, for each bounce of a ball. What is the average rebound percentage for the ball if the original height is 72 inches? Okay, so we're given all the information we need. And we still got to clear this information off from where we're working earlier. So the average of the rebound, a percentage, is the ratio of the bounce to the drop height, or the new bounce from the last bounce, okay, which we typically will do. It'll be the bounce in the front over the bounce that was in the back. So let's look at that. In other words, it's 28.8 divided by 72. That's 0.4 or 40%. So that specific bounce is a 40% drop height, okay? Or a 40% rebound percentage. Now let's look at the next one, which will be 11.52 over 28.8. So 11.52 divided by 28.8. It's also 40%. Okay, so how about the third bounce height, 4.6 over 11.52. So 4.608, 608 divided by 11.52. It's also 40%. Finally, the fourth bounce over the third bounce, which is how we find the ratio, 1.842 divided by 4.608, 4.608. Enter. Comes up to 0.4. So 3.999,99739. It rounds up. So let's see what our answer is. We've just shown that it should be all 4. And the way I've done this is I've looked at each one and I've determined that, let's look at this. I've determined that by finding the rebound percentage of all of them, that's not right. This should be blue. Lord have mercy, it's messing with me bad. Here we go. Changing the wrong thing. Okay, so we should have the rebound percentage of the rebound ratio of 1 over the first bounce over the drop height is 0.4. The rebound percentage or the rebound ratio of the second bounce over the first bounce is 0.4. The rebound ratio of the third bounce over the second bounce is 0.4, and the rebound percentage of the fourth bounce over the third bounce is 0.4. So the average rebound percentage, since they're all the same, is 0.4. Or the rebound average percentage is, or the rebound ratio is 0.4. Rebound percentage is 40%. So the way we would do that, if they were different numbers, if these were all different numbers, the 0.4s, we would add them all together and divide by the number of ratios we got. In this case, there's 5 numbers. The differences or the ratios between them are, there's 4 of them. And we can easily determine that adding those 4 together, if we were to add 0.4 together 4 times, we get 0.4 plus 0.4 plus 0.4 would be 1.6. If you divide 1.6 by 4, which is 4 values, you'd get 0.4, so 40%. All right, folks, thank you very much. I appreciate your time on this matter. Be prepared to take this test and get it done right away. And in the meantime, y'all, be blessed, be a blessing.